That last one was pretty intense. Let's work a pretty simple example here. Again, we're going to draw shear moment diagrams. Let's say I've got a fixed support this time, and we'll keep this one generic. Let's say I'm going to apply some load force P, just some push force, and we'll apply it at some distance L. And again, a fixed support over here. And again, the goal is going to be find the shear V and moment M diagrams. Okay, or draw shear moment diagrams. Okay, well, step one, of course, is to find your reactions if you can. So if I call this point A, and notice that I'm applying force P over here. So I've got a fixed support here. I would have an X, Y, and reaction moment. There's no need to draw an X because there is no X loading forces. So I have a force P to counteract this one. This is going to cause a reaction this is going to cause a clockwise moment. So I would need a reaction moment L times P. Now I'm skipping a bunch of steps here. Feel free to pause and work this out by hand. I'm going to show you that you can actually work this one just by kind of looking at the diagrams and approaching it accordingly. So now I'm going to do it with just generic numbers, but this is my reactions. Right. This shows me my reactions. So now I know my forces. That was step one in the shear moment diagram process. Find your reactions if possible. Found my reactions. Now, using those reactions and any applied loadings, determine how many places you need to cut through this beam. Well, I've got reactions on the end, and I've got a loading on the other end. And that's it. So basically, the shear and moment are going to have the same expression from one end to the other. There's no change. There's no change in distributed load. There's no forces applied in the middle anywhere. So literally the only thing occurring here is reaction on one end, applied on load on the other. A single cut through this is all I'm going to need to actually determine what this looks like. So one cut, arbitrarily at some distance x, applying a force P and the reaction moment LP, and then I've got shear and bending moment applied at distance x. So I'm going to have one cut there. Okay. So what you're going to find, if I add up forces in the y direction, set those equal to 0, then you're going to have P minus shear, and that's going to have to be 0, so your shear is just going to equal a constant P. Okay. And whenever you've got, basically whenever you have no distributed load, you're going to have a constant shear force. Because again, the distributed load would be the derivative of the shear. Well, that means that if I have 0 distributed load, that means I'm going to have constant shear. If I have constant shear, I would have just a 0 distributed load. Now the sum of moments about point A add up to be 0. I've got this reaction moment, which equates to LP. That's positive. I also have the reaction moment M, positive. And then I have minus whatever the shear is at distance x. So my shear, my moment, my bending moment, is going to equal shear times x. Well, my shear is P, so this is going to be P times x. And it's going to be, I'm going to move this over to the other side of the equation, so it's going to be minus LP. So P times x minus LP is going to be my equation for moment. So P and L are all constants. X is a variable. So this is a linear equation with a positive slope. Now what will happen then, and if you notice, we've done previously, of course, this goes from x is a value of 0 out to a maximum value of L is the range for these equations. So that means M at 0, of course, is minus LP. M at a distance L is going to be 0. Those are the limits for this equation at these limits for x. So it's going to tell me what my graphs look like. So my shear is just to be a constant P. So if I plot my shear as a function of x, right, so I'm lining this up here, and notice that I've got this reaction force P, so it's going to take it up to a positive P. So in theory, I wouldn't even necessarily have to find this. I could look at my reactions and say, you know what, I've got a force here going to push it up to a value P. There's nothing in between here changing it until, so it's going to stay constant P until I get out here to this point where I'm going to have then this force is going to push it back down to 0. This is my shear as a function of x. And then my moment equation, or my moment diagram, notice my values for moment they're going to start at a minus LP and they're going to go up to 0. So if I plot an x is equal to 0, or I guess y, this is my 0 point, down below here I'm going to have minus LP. And notice what's going on here. I've got this reaction moment that's actually going to end up causing my bending moment, because this is positive at this point. That means my bending moment's going to have to counteract that. So my bending moment picks up a negative sign. So it starts out here at minus LP. And then it's going to go, notice my equation here has a positive slope. So I have a positive shear through here. Remember, shear is, or the derivative of, so shear is the derivative of moment. So if I have a constant shear, positive constant shear, that means I'm going to have a positive slope linear equation for moment going from LP to 0. Notice my value for shear is positive P. The slope of my moment equation is positive P. This is my moment diagram. So you can, to an extent, just simply from here say, well, you know what? The shear is going to get pushed up by P. It's going to get pushed down by P at the end, and that's going to be my shear diagram. My moment, it's going to get pushed down to counteract this positive moment here. It's going to start out down here. And because there's no distributed load in between here, it's just going to cause a constant. And since I've got a positive P, that means I'm going to have a positive linear slope, a positive constant value here. I'm going to have a positive linear slope on my moment equation there to get out to the end. All right, I did that one kind of quick, but I promised you it's a simple short video because the last one was pretty long and intense. So that's pretty close to a full lecture. We really should work one triangular distributed load, and I think that's probably good for shear moment diagrams at this point.